All right. Okay, so let's start. So goal is to use quantum espresso or QE to compute the band structure. Band structure, okay? So now the question is, what are these things? What are the band structure? Plus, what are the things we need to understand, how to interpret the band structure, use it in some calculations, uh, and how to make the calculations accurate. Okay. So এই জন্য বলেছিলাম যে maybe we can start with quantum harmonic oscillator. Quantum harmonic oscillator. So the idea was we bands যে টার্ম এটার অরিজিনটা কি ওইটা একটু ভালো মতো বোঝা। সো সো আমাদের যে সফটওয়্যার লাগবে তার একটা লিস্ট দিয়ে নিই, কারণ প্রতি সপ্তাহে কিছু না কিছু অ্যাসাইনমেন্ট থাকবে, লাইক সিম্পল স্টাফ মোস্টলি। প্রথম সপ্তাহের অ্যাসাইনমেন্ট মোস্টলি সফটওয়্যারগুলি ইনস্টল করে লাইক ফাংশনাল রাখা, যাতে নেক্সট উইক থেকে আমরা ট্রাই করতে পারি। সো হ্যাভ ইউ গাইস এভার ইউজড SSH সিকিউর শেল? Okay, okay. So this is, you probably need to learn a little bit, because Quantum Espresso, এটা একটু kind of heavy software. So meaning তুমি যদি ক্যালকুলেশনটা অ্যাকুরেট করতে চাও, then you need more computational power, more RAM, sometimes VRAM. So usually পার্সোনাল কম্পিউটারে ওরকম পাওয়ার থাকে না সাধারণত। সো তোমরা নিজেদের কম্পিউটারে সেট আপ করবা কোয়ান্টাম এসপ্রেসো। সো কোয়ান্টাম এসপ্রেসো ইন পার্সোনাল computers. That's what you need to test simple systems. Okay. Then in powerful server to do actual computation. Okay. So this is something you can do. কোনো একটা সিস্টেমের জন্য আমরা সিম্পল সিস্টেম চুজ করব, যে সে জাস্ট সিলিকন ইজ এ স্ট্যান্ডার্ড এক্সাম্পল। পার্সোনাল কম্পিউটার রান করার জন্য ইট কুড টেক কাপল অফ আওয়ার্স মেবি। There was a question in the chat. Okay, I will answer that question. পার্সোনাল কম্পিউটারে ইউজ করা যাবে, তারপরে যখন আমরা একটু লাইক ফাইনাল অ্যাসাইনমেন্ট যেগুলো থাকবে সেগুলো ট্রাই করব, দেন ইউল নিড লিটল মোর পাওয়ারফুল কম্পিউটার। নাও আই হ্যাভ এ সার্ভার, সো এটা অ্যাক্সেস করার জন্য ইউ নিড SSH. So you also need to learn that. I think I have a list of softwares that we need. So আমি যেটা করব, ডিসকর্ডে মানে কোন কোন সফটওয়্যার লাগবে সেগুলি একটা লিস্ট আমি হয়তো পোস্ট করব। এগুলো দেখা শুরু করবার প্রবলেম হলে নক দিবা। নট জাস্ট মি, তোমরা কিন্তু করতে পারো যে ইউ ক্যান আস্ক ইচ আদার, রাইট? সো রিসার্চে একটা খুবই ইম্পর্টেন্ট পয়েন্ট হচ্ছে দ্যাট উই কোলাবোরেশন ইজ রিয়েলি ইম্পর্টেন্ট। কারণ লাইক সিঙ্গেল অথর পেপার ইজ কাইন্ড অফ এ হিস্টোরি নাও। এখনকার সময়ে সিঙ্গেল অথর পেপার সাধারণত কেউ করে না বা পসিবল হয় না। ইটস লাইক বিকজ দেয়ার লট অফ থিংস ইনভলভড। ওকে, কোলাবোরেশন খুবই ইম্পর্টেন্ট। সো একে অপরকে হেল্প করবা। আমি তো আছি, হোপফুলি প্রবলেম হবে না। So this will be my server. Okay. So question was from Alvi. Uh, we need Linux OS for Quantum Espresso. Not necessarily. Quantum Espresso Windows install করা যাবে, but personally I prefer Linux. Plus যে সার্ভারের কথা বললাম, my server, this one, is also a Linux server. লিনাক্সটা for few things Linux is better, I think. Well, that could be personal opinion, or but yeah, I think you can also install it in Windows. So try করে দেখো Quantum Espresso website. What is the website? quantum-espresso.org. Okay. I'm gonna post this link. Maybe you know this, but in the Discord, I'm gonna post it anyway. Okay. So that's the website. From there, you can download the software and try to install it, see how it goes. So the softwares we'll need, our goal is to use Quantum Espresso. We all also need, um, Python. Why? Because to plot the data and sometimes to analyze things, we'll need Python. So I prefer Conda installation, but any installation is fine. Um, try to learn virtual environment. Okay, মানে পাইথনে ভার্চুয়াল এনভায়রনমেন্ট তৈরি করা যায়। সো এটা কিভাবে করে একটু দেখার চেষ্টা করো, দিস উইল বি এ গুড থিং। নাম্বার 3, as a text editor, I think VS Code is better. কারণ হচ্ছে VS কোডে তুমি পাইথন ইউজ করতে পারবা। পাইথনের আরেকটা কাইন্ড অফ কি বলে ইউজার ইন্টারফেস আছে, গ্রাফিক্যাল, আই থিঙ্ক জুপিটার নোটবুক, প্রবলি ইউ হার্ড অফ ইট। সো সেটা ভিএস কোডে ইউজ করা যায়। প্লাস আমি যে SSH এর কথা বলছি, my server, you can also use VS Code to access my server using SSH. So that's the good thing. That's why VS Code is kind of probably like you know a good text editor. Then what are the other softwares? Let me just look at it. Um, and we'll need to read papers. So maybe you can try Zotero software. That's optional. Zotero is optional, but everything else is kind of, we will need that. Um, yeah, these are more or less all the softwares we need. If we need more, I'm gonna let you know. Well, another thing is, I think the GNU plot. So sometimes just after running Quantum Espresso, you just want to plot it right away. And if you have a GNU plot script written, you can just run it and it will generate the plot. It could be an easy solution for like a lot of things. That's also optional. Okay. Any questions so far? Okay. All right. So I guess we'll have like about 12 live sessions, maybe a little more. So in our first day, maybe we can start with like, answering the question, what are the bands and how do we get it, like the origin. But এটা তো কোয়ান্টাম মেকানিক্সের বা সলিড স্টেট ক্লাস না, সো কিছু ডিটেলস স্কিপ করতে হবে, বাট তোমরা যদি কোয়েশ্চেন করো দেন উইল গেট ইনটু দোজ ডিটেলস, বাট আই জাস্ট ওয়ান্ট টু গিভ ইউ দ্য বেসিক পিকচার, রাইট? ওকে, সো let's start. Quantum harmonic oscillator. Okay, so what is a harmonic oscillator? Is basically if you have for example, a mass spring system. You have a spring and a mass attached to it. So now this mass can oscillate. So displacement from equilibrium, if that's x, and the spring constant is k, x is displacement from equilibrium. K, spring constant. So question is, what is the total energy? E total. What is the total energy of the system? Um, yes, I couldn't understand you if you had said anything. I'm sorry, but audio is not understandable for some reason. Half kx squared, yes, that's one of the term. So kinetic plus potential energies, right? So what is the potential energy? Half kx squared. And what is the kinetic energy? Half mv squared, right? এই পর্যন্ত কারো কোনো কোয়েশ্চেন, প্রবলেম or any confusion? Because এটা very important যে আমরা like we are starting from here. This is our starting point. Okay, যদি কারো কোনো কোয়েশ্চেন থাকে, you have to ask. You cannot hesitate. Okay, no one like যদি মনে হয় যে maybe this is a really simple question, everyone knows the answer, I don't, maybe I shouldn't ask. যদি তোমার মনে এরকম কোয়েশ্চেন হয়, there must be someone as well having the same doubt. Okay, just ask. Okay, so if there's the kinetic energy, there's the potential energy, we can write it in a different form. P squared over twice m plus half m omega squared x squared. The reason we can do that is P equals mv and omega omega squared equals okay, let's k equals m omega squared. Okay. Oh yes, thank you. P squared over twice m. Okay, that's our total energy. Now, in quantum mechanics, we have a operator quantity called the Hamiltonian. Hamiltonian is basically this total energy. Symbol is H. So P squared over twice m plus half m omega squared x squared. But in quantum mechanics, this Hamiltonian, this P and this X, they are operators. This hat means, okay. in quantum mechanics, these are operators. Twice m and half m omega squared, these are numbers. Okay, so now we have the Hamiltonian operator. The question is, how do we solve the system? We have the Schrodinger equation. We can solve the eigenvalue equation, h psi equals e psi. We can solve the differential equation and find all the energies, or we can solve it using operator method. So there are more than, I think, two methods, but two famous one is, first one is polynomial method. For harmonic oscillator, you get something called Hermite polynomial. And another one is operator method. Uh, we get creation and annihilation operator. Creation is A dagger, annihilation is A. So we're gonna use this method, the operator method. So to solve this system, you see in the Hamiltonian, let me copy this Hamiltonian over to next page. So this Hamiltonian is nothing but the total energy of the system. So dimension of this Hamiltonian is energy. And if you have solved harmonic oscillator before, or have taken any quantum mechanics course, you know energy can be written like this: h bar omega. H bar is the reduced Planck constant. Omega is the frequency, angular frequency. And h bar equals h over twice pi, and h equals the Planck's constant. Okay. So that's the unit of energy. Now, to do these kind of analysis, one good thing is to express all the quantities in dimensionless unit. So see, h has the unit of h bar omega. If we divide h by h bar omega, what do we get on both sides? 1 by twice m h bar omega p hat squared plus m omega squared over twice h bar omega. Is that okay? If I make mistakes, please let me know. Okay, so let's call this quantity on the left side h tilde. Okay. And we have p squared here. 1 over 2 m h bar, let's write it like this: p hat m h bar omega square root square plus, here omega cancels out, we have m omega over h bar square root x squared, and we also have, we can write it like this: half p tilde squared plus x tilde squared. Any questions so far? That's p tilde, and that's this whole thing is x tilde. Any questions? Okay. So now that we have x squared and p squared, we can try to, if possible, factor the two squares, like, a plus b into a minus b, but there's a plus there. That's the problem. So if we had, say, p squared minus x squared, we could have written like this, p plus x, p minus x. But we have a plus there, so we cannot really write it like that. But if we introduce imaginary number I, complex variable, then maybe something can be done. Yeah, Shornali asked, why is it necessary to make it dimensionless? Good question. So in regular quantum mechanics class, usually they don't express it in dimensionless quantity. But my experience is that when you express it like this, things become simpler. You don't have to worry about all the factors. I don't know, for some reason, m h bar omega square root, this factor kind of, I don't know, stares at you. I like it simpler, you know, and it will make the equation look cleaner, as you will see. And since we'll have all the quantities here, h, p tilde, and x tilde, they are just numbers, pure numbers. When they are pure numbers, working with them is way easier. Okay, so now that we have x squared and p squared, x tilde squared, p tilde squared, what can we do? Remember the quantities, the creation and annihilation operator. So for, okay, we're going to define that. The annihilation operator is defined like this. X tilde plus I p tilde, and creation operator 1 over square root of 2 x tilde minus I p tilde. And okay, we have two operators. We have a plus b and a minus b, right? What happens if we take a product? Because remember, our goal was, if we have a squared minus b squared, we can write it like this: a plus b, a minus b. And this is in second order, a squared, but this, we have two different factors, both are in first order, and that is an advantage in solving system. If you have quantities operators in first order, that can simplify calculations. Okay, so what happens if we take their product, say a dagger a, half because of the square root, and then x tilde minus I p tilde, x tilde plus I p tilde. And then we have x tilde squared plus p tilde squared. What else do we have? We have the cross terms, right? So x tilde p tilde minus p tilde x tilde. We have this cross term, half x tilde squared plus p tilde squared plus I x tilde comma p tilde. This is called quantum mechanical commutation relation. X comma p, or let's write it like this: a comma b is AB minus BA. Let's say that's our definition. Okay. How it comes to be from classical mechanics, the Poisson's bracket, the general definition is complicated, but if we just use it as our definition, we can still almost do everything. So x tilde comma p tilde means p minus px. Important thing is for pure numbers, if we have a and b, two quantities, and they are pure numbers, then ab minus ba is 0 if a and b are numbers. But if they're operator, then that's not the case. If a and b are operator, then AB not equals to BA, meaning the order matters. আমরা কি সবাই এই কনসেপ্টের সাথে পরিচিত যে order matters for operators? If not, I can explain. Okay, always familiar with this. Okay, I guess everyone is more or less familiar. So যদি confusion মনে হয়, just consider them as matrices. If you consider A as a say 3 by 3 or 2 by 2 matrix, 1 2 minus 1 5, and B 3 minus 2 0 2, if you multiply them like this, AB, that's not going to be equal to BA. If you change the order, they're not the same. They don't have same product. Order matters. And the question is, what do we do about x tilde comma p tilde? Now we have a canonical commutation relation. Which is just x comma p equals I h bar. This is, say, given in quantum mechanics. Okay, we can actually prove this, but that's not the point of this course. So let's just say this is given, and we're going to use this to evaluate x tilde comma p tilde. So if you remember, this is p tilde, that's x tilde. Let me copy it. Let me copy the whole Hamiltonian. So x tilde comma p tilde equals x m omega over h bar square root x comma 1 over m h bar omega square root p. Okay, x, this is x, and this is p. Okay, like, so that you can match the colors, might be easier. And when you have a commutational relation like this, the rule is if a comma b are, say, real numbers, this bold r means they are real numbers. They can be complex, but let's say they're real. Then and a comma b are operators, then small a times big A, comma, small b times big B. This can be written as small a, small b as a product outside the commutation relation times a, comma b. Let's say this is our assignment 1.1. Okay, like proving this. So their product here will be m omega, and omega cancels out. So we'll have 1 over h bar, x hat, comma, p hat. And x comma p is ih bar. So we just have I, x tilde. Not too bad, right? I mean, x comma p was ih bar. H bar is a quantity with some dimensions, a constant with some dimensions. But I is just a number, complex number. So x bar, x tilde and p tilde, their commutation relation gives you just I, which is kind of expected that we'll get something dimensionless, and we did. So this is just I. That means here, a dagger A, let me copy it. And we're going to use it here. Have x tilde squared, p tilde squared, plus I, and this is also I. Have minus 1, because we know in complex numbers, I is square root of minus 1, and I squared is just minus 1. So what do we have? We have x tilde squared plus, oh, all right, we can do this. Just write it like this, plus p tilde squared minus half. And if you remember, this is nothing but the Hamiltonian. What is the definition of Hamiltonian? Hamiltonian is p tilde squared plus x tilde squared. So we can just write it here that we have the Hamiltonian minus a half. So Hamiltonian equals a dagger A minus plus a half. If you take the half to the other side. Okay. Any questions so far? It's okay. If you have question, you have to ask. Okay, good. So this is the Hamiltonian. So we have more than one expression for the Hamiltonian. You can express it like this, or like this. Or sometimes a dagger minus a half. Yes, there's a physical significance of the last expression, and I'm gonna get in there basically now. So we can write Hamiltonian in multiple ways, but this particular expression is kind of really useful, because if you remember, h tilde is a dimensionless quantity, just a number. Half is just a number. So a dagger A is also just a number. right? Because we expressed everything in dimensionless quantity. If you compute the unit of a dagger A, you'll see it's dimensionless quantity. So we define another operator called the number operator, which is just capital N, defined like this, a dagger A. Okay. And then Hamiltonian can be written like this, N plus a half. Let's put a tilde there. Okay. N is the number operator. And the usefulness of this number operator is, so in a harmonic oscillator, remember we have a single oscillator. We have a single oscillator with one mass and one spring only. So this number operator will tell us what's the uh, the energy of the harmonic oscillator, or the state in which, like, it gives us this number of what do you call it? So if the harmonic oscillator is in state N, the number operator will give that as an eigenvalue. Okay. So are you guys familiar with the bracket notation? Okay. Okay. So simply saying ket is this symbol, which is like a column, and the bra is like this, which is like a row. Column vector, row vector. They can be something more complex, but this is a kind of a simpler interpretation, all works most of the time. So this N is the state of the oscillator, and the eigenvalue equation for N is, if we do this, apply the operator, we call it like this, apply or act on N by N. We get back the same vector times a number. This is operator, this is number. So that's why it's called a number operator. We get the number back. So the question Shornally asked is h equals n plus half. What's the significance? And if we apply h to this state, we have n plus half applied to the same state. Next line, we get small n. These are numbers. Small n is the number, big N is the operator, n plus a half, and then we get big N here. So remember, H tilde is H over H bar omega. So small H would be, the Hamiltonian would be H bar omega times H tilde. So H bar omega, H tilde would be N plus a half. Uh, okay, so that's the energy of the harmonic oscillator. Um, for let's call it uh, E N. So En would be like this, energy of the harmonic oscillator. And we can prove that N is always greater equals 0, and N is an integer. So it's Z. That means N can be 0, 1, 2, up to infinity. That means the lowest energy or the ground state of the harmonic oscillator is half H bar omega, ground state. And excited states will be separated by an integer multiple of H bar omega. So the way the picture is drawn is like this. That that ground state is here, and the energy there is not 0, rather is half H bar omega at this point. And next excited state would be, so this is the ground state, N equals 0. The next excited state, N equals 1. Energy there would be 3 half H bar omega, because if small n equals 1, then 1 plus a half is 3 half. So we have, 3 half H bar omega. That's how it goes. We get the energy levels. So I'm not solving for wave functions or solving the differential equation right now, but I just wanted to show you that for a simple harmonic oscillator, this is what we get, the energy levels. Like they're separated by integer multiple of H bar omega. Okay. Any questions so far? Now, I guess I can give you homework on solving the wave function, but that's not the goal of our of this, um, course. The goal is to how to use quantum espresso. So the homeworks would be a little different than regular, classes, I guess. Now, if there are no questions, then maybe I can move to next part. Good question. How does it relate to band structure? That's what I wanted to do. Yes, Pallav had also a question.
Yeah, I just wanted to ask that here we get no state at zero. Is there any physical intuition to that or any significance?
Good question. So the, there is always something called the ground state or the lowest energy state. And for quantum systems, Classical system, if the oscillator is not oscillating at all, then that's the ground state, stable. No kinetic energy, no potential energy. It's not oscillating. But in quantum systems, it seems that you cannot have a zero energy state for harmonic oscillator. There's like a finite energy, which is h bar omega, and it's something always there. So, remember the Heisenberg uncertainty principle that if you measure the position of a particle precisely, the momentum becomes, kind of really big or not predictable because there is a product of delta x and delta p, which is greater or equal to, h bar or h bar over 2. So if you measure one quantity, another quantity becomes unstable. So in quantum mechanics, things don't always follow what we intuitively think. And here, the ground state energy is not zero, rather something finite. That's the kind of the point I think here. And what's the physical significance? So I guess there's something called a vacuum expectation energy. This is not probably directly related, but in a vacuum, you think there is no particle at all, perfect vacuum, right? But scientists have measured fluctuations in vacuum, meaning particles and antiparticles would appear out of nowhere and then annihilate in a few moments, and it will keep going. So in quantum mechanics, things are a little weird. Um, so yeah, the minimum energy state for harmonic oscillator have finite energy, which is non-zero. That's the significance of this harmonic oscillator. And this simple system shows something unintuitive from classical mechanics. From classical mechanics, you'd think that ground state energy would be zero, but in quantum mechanics, it's not. Okay, does that somewhat answer your question?
Yes, it gave me some perspective. Thank you.
Okay. And then Alvi asked, how does it relate to band structure? Let me just give you brief overview. So we have, simple one oscillator, right? We have one oscillator, and while one oscillator have energy levels. Now, instead of one oscillator, we can have two oscillator or coupled harmonic oscillator. And we'll we'll get energy levels, but they're not the same. So let's say this is En, but when you have two oscillator, the total energy would be energy for the first oscillator plus energy for second oscillator, EMN. Okay, does it make sense? You have two oscillator, total energy is like a sum of the two. And instead of writing equal, let me write it like this, because there is a constant term somewhere here, which is not zero. So, it's not just sum of the two energy. There's a constant there, plus C. Meaning, even if the both oscillator is in ground state, the energy would still be something little greater than half h bar omega from both of them. And they can have different frequency. You see, when you have two coupled harmonic oscillator, both can have different frequency. and system would be a little complex in that case. Now, you can have one oscillator, two oscillator, or you can have one dimensional chain of harmonic oscillator. Infinite chain. So it's like this. You have one oscillator, you have two oscillator coupled, and you have infinite chain of harmonic oscillator. And in that case, this energy would be like sum of many things. Okay. Sum of it's not just sum of individual energy. Things get complicated. And these are called the bands. Does it somewhat make sense? Now, for when we just consider their vibration, oscillation, then these bands are phonon bands. What is a phonon? Phonon is I couldn't understand what you say. I think the audio wasn't clear. Uh, could you repeat or just type the question? Vibrational lattice position. Yes, exactly. So you see the how it goes. A single oscillator, we get energy levels, and we have somewhat solved it. We found the levels. We can have two coupled harmonic oscillator. Again, we can have energy levels. And when you have infinite chain of harmonic oscillator, we have something called bands or phonon bands. Bands for phonons. Like phonons are quanta of lattice vibration. So these are bands. It's, when we have a repetitive system, a lattice, and all the lattice can vibrate, then their energy, they are called bands. And it's not simply sum of all the bands, it gets a little complicated because of the interaction. Now, this is one-dimensional chain. What happens if this is a three-dimensional chain? If it's a 2D chain or 3D chain, things can get really complicated. So that's where quantum espresso comes in. We can compute bands for complicated system. Okay. Now, we can have phonon bands or not or and electronic bands. So phonon bands, the origin for those are vibration of lattice points. For electronic bands, the origin is the electromagnetic interaction between electrons of different sites. Okay, and there's a model called the tight binding model. Um, I don't know if we want to solve those models in details in this class, but we'll certainly discuss it a little bit. Okay. For electronic bands, for a single atom, we have um, again have energy levels, right? So hydrogen atom, we have electron moving here. No, electron is not a particle and it's not a wave. It's a quantum system. So it behaves like a particle, sometimes like waves, but it's neither. It's quantum. There's no classical analogy, but assuming their point particle helps interpreting a lot of things. So let's say this is a single electron and there's two let's say this is just, it's not hydrogen. Let's say this is just an atom. Okay, so like this. And another electron there. And for a single atom, there could be energy levels like 1s, 2s, 2p, 3s. These are the electronic configuration, right? They have different energies. Are we familiar with this thing? Like for a single atom? Okay. Now, for a single atom, we have different energy levels. For two atoms, we can all again have energy levels. And for okay, I think let me write it here. One atom, point two is two atoms, and their levels will be mixed, not the same as before. Okay, so these are energies, and again these are energies. Instead of two atoms, when you have infinite chain in lattice, you have something called electronic bands. Their energy levels, okay, combined. Like the problem is in a crystal, we want to have a way to explain their behavior as a whole. Like, we don't want to talk about a single atom because in a lattice there could be, in 1 mole there's 10 to the power 23 atoms. So in a lattice, millimeter size lattice, there could be way more. I don't know, maybe 10 to the power 27. So we don't want to talk about individual atoms, but we want a system, a model, so that we can describe all of them, with a simple model. And that model is these bands. Well, if we consider all the atoms, all the interactions, what do we get? We get electronic bands. And those bands help us to understand how the material would behave as a whole. Will it be a conductor? So can tell us, is it an insulator or conductor or superconductor? No, semiconductor. Superconductivity is a little complicated. You need something more than just bands, but it can tell you a lot of things. And if it's a semiconductor, is it a p-type or n-type? Which one dominates, electrons or holes? It can tell all of those from the bands. And we can also calculate their resistivity, thermal conductivity, and their thermal power, or Seebeck coefficient. We can also, explain the density of different charge carriers. Um, Charge carrier density, and a lot of things. Okay, so these bands can tell us a lot of things, like how they interact and at which temperature which band will be more contributing to their thermoelectric properties, or other properties like topological properties. Some bands can show some topological invariance and give you topological behavior. So understanding these bands is important. You don't have to know all the details, but some idea so that you can navigate your way and extract the information, maybe read some papers to understand what's going on. That's important, because say if you want to know how the quantum espresso was written, the code, that's going to take a long time than 3 months, maybe few years. But just using the quantum espresso, having the basic idea is probably doable in few months. Just the basics. Okay. Um, any questions? Now, I can explain how we compute the energy for coupled oscillator and then one-dimensional chain of harmonic oscillator, but I don't know because all of you don't have the same background, so I'm kind of trying to decide which way to go. But I think we need the idea of Brillouin zone because you see these energies, um, this energy, and when you have infinite system, these energies they're not function of position, rather they're function of lattice momentum or k, and the range of those k is determined by the Brillouin zone. So probably it's a good idea to review one-dimensional chain of harmonic oscillator a little bit so that you have an idea of Brillouin zone and why these energies as a function of k, this E is a function of k. That's kind of important. And then um, we can compute um, after maybe after this one-dimensional chain of harmonic oscillator, we can talk about parabolic bands and how to compute the density of states for that band. What is the density of state? What are those? Those are also important. Okay. Uh, yeah, I think in our next class, probably we're gonna discuss this one-dimensional chain of harmonic oscillator. Still trying to decide. I need your feedback, guys. So I'm gonna post this note in Discord, and you can review the note and try to rederive some calculation. There's the assignment there. Probably I'll also post another assignment. So for first week assignments would be number one. Uh, what is that assignment? There's one. Yeah, this thing. This is assignment 1.1 and prove this. Um, I think it's better if I write it cleanly and then post it, but let me just give you a rough overview. And two would be um, okay, so um, node with okay. So whatever I've shown today, you want to make your own note with details calculations, you'll have my PDF available. So what you're gonna do, you're gonna, sometimes I've said things, but I haven't written anything, and you may have questions, and sometimes things can be a little different in your mind. You want to write it down so that when you come back a few months later or a few years later, you can always refer back and remember what you learned before. So you want to make your own note. That's also an assignment. And number three would be install Quantum Espresso uh, and install Python. And what else? What are the other software? SSH, right? VS Code. install VS Code, and for now, I guess this is it. But number four, uh, learn about SSH. So this is just try to review what is SSH. This is like optional. Um, it's not it's not optional. It's basically we don't need it right away. Maybe after 2 weeks or a month, depending on like your progress. When I see that you guys are ready to use the server to compute the band structure, then I would give you access, and then you need to know how to use SSH. But you need to learn how to use Linux terminal. You can try VirtualBox. Have everyone used the any Linux operating system before, like Ubuntu or Fedora or Red Hat or anything? Okay. Okay, so I guess uh, I need to show you a little bit uh, because you need a platform to practice how to use Linux, and that's going to take time. I cannot just give you a lot of assignment and then expect that you know everything within a week. That's not the way it works. So it's like a little bit at a time, but you guys need to communicate, okay, to with me and with each other. Uh, okay, so let me stop sharing this screen and uh, put it stop share. I'm doing stop share, but it's not working. Uh, okay, now I can share my screen here. Uh, Desktop. Okay, can you guys see my screen? Uh, okay. So there's something called VirtualBox, Oracle VirtualBox. You can try that, and Ubuntu system. So try to download this Oracle VirtualBox. Go to download and download. If you have a Windows machine, download for Windows. If you have Mac, Intel, or Apple Silicon, download all of these. And if you already have Linux, then you don't need to do anything. You can download the Ubuntu, manage tracker, save preference. From here, download Ubuntu desktop, and then it's like a 6 GB file. So the way it works, you can virtually install this operating system, Ubuntu, in this virtual box. And then you can use it, try different commands, practice things. Okay, so I'm gonna post this link in Discord after the meeting, and you can try to install. If you get stuck, you can post it in the Discord. Maybe we can have different channels. Like one channel is just for announcement, like where I post assignments or instructions from me. Another channel is just for our interactions. Like you have any questions, you can ask, and you guys can talk to each other privately. I guess is fine. So if you face any problem, you can take a screenshot and then ask me questions or post it in the group. We'll try to answer the question. And yeah. So, any more questions today? Okay. Okay, so you're at the end of our today's meeting, I guess. So, I think if you guys can have a good like audio system, like you can talk, it could be a good thing. I mean, you can always, do it in chat, but today it was kind of simple things, but in future it could be a little more involved. Uh, sorry guys, মানে মাঝে মাঝে কথা বলা শুরু করলে ইটস লাইক অটোমেটিকলি ই হয়ে যায়, ইংলিশ হয়ে যাবে। কমিউনিকেশনের প্রবলেম হলে আমাকে বলবা, আমরা বাংলা ইংলিশ মিক্স করেই করব, নো প্রবলেম। ওকে, সো আজকের মতো তাহলে এখানে আমরা হয়তো শেষ করি, যদি কারো কোনো কোয়েশ্চেন না থাকে। সো হোমওয়ার্কগুলি বা অ্যাসাইনমেন্টগুলি আমি ডিসকর্ডেও বলবো, ডিফারেন্ট চ্যানেল একটা আই থিঙ্ক তৈরি করব, আর এই পিডিএফটা আমি শেয়ার করব। তোমরা ওই অ্যাসাইনমেন্টগুলি করা ট্রাই করো, কোনো প্রবলেম ফেস করলে বলবা। আর একটা কোয়েশ্চেন আমার ছিল, তোমাদের কি লাইক এখন কোনো মানে ক্লাস হচ্ছে বা কোনো এক্সাম আছে সামনে? যদি এরকম হয় আমাকে কিন্তু বলতে হবে, হ্যাঁ, সো দ্যাট উই ক্যান রিস্কেডিউল, and if you need any kind of help, you need to just ask. আর ইয়া, অডিও সিস্টেমটা যদি একটু ভালো হয়, কথা বলতে পারো, তাহলে আই থিঙ্ক বেটার হবে ফিউচার সেশনগুলোতে। ইয়া, ইয়া, you're welcome. Um, so I think you guys have some idea of what are the bands, like some direction, where are we going? So কোয়ান্টাম এক্সপ্রেস সফটওয়্যার যখন আমরা স্টার্ট করব, লাইক আমি দেখাবো যে আসলে হাউ ইট ওয়ার্কস, তখন এরকম একটা ওভারভিউ দেওয়ার চেষ্টা করবো যে আসলে what are the inputs, what are the outputs, how it works, how to kind of navigate your way through it, how to find the pseudo potentials from the website, and I think আমরা কিছু টয় মডেল সলভ করব পাইথন দিয়ে। হ্যাঁ, টয় মডেল সলভ করার কারণ হচ্ছে যে কোয়ান্টাম এসপ্রেসো ইন দ্য ব্যাকগ্রাউন্ড, হাউ ইট ওয়ার্কস, দ্য ডিটেলস that's really complicated, but the basic idea আমরা একটা টয় মডেল দিয়ে বুঝতে পারবো হয়তো, যে this is something called pseudo potential, this is the wave function, এইভাবে সলভ করি, this is the charge density, so how things work, okay, টয় মডেল। আর তোমরা কি গিটহাব ইউজ করছো কখনো? গিটহাব, that could be something useful, um, like যখনই কোনো কোলাবোরেশন করা হয়, ইট কুড বি ইউজফুল। আচ্ছা, ওকে, আমি ইউজ করার আগে অবশ্যই দেখাবো যে হাউ টু ইউজ ইট। ফর নাও আই গেস আই এম গোনা পোস্ট on Discord things that you need to try. See, research কিন্তু it's not, you try it once, you fail, that's fine. Research is you try it again, analyze why you failed, try it a little bit differently so that you can succeed next time. That's research. Okay. Like you have to try by yourself, ask questions to someone who knows, who might know. Okay, it could be important. Failing is fine, but you have to keep trying. Um, okay, I guess that would be all for today. So আমাদের সেশনগুলি হয়তো এরকম um, 1 ঘন্টা 1.5 ঘন্টা, মাঝে মাঝে 2 ঘন্টা হতে পারে, বাট আমি চেষ্টা করবো এর চেয়ে বেশি না হওয়ার জন্য, বিকজ আই থিঙ্ক মানে আহ, একটা টপিকে খুব বেশি সময় ধরে ফোকাস রাখা ডিফিকাল্ট হতে পারে, লাইক ফর মি অ্যাজ ওয়েল, লাইক ইফ আই কিপ টকিং ফর 2 hours it could be difficult, right? Okay, so hopefully we'll see you. We'll meet each other next Saturday, same time. Uh, hopefully in Zoom. জুমের সুবিধা হচ্ছে আমি আমার স্ক্রিন শেয়ার করে ওখানে লিখতে পারি। আই ডোন্ট নো এই ফিচারটা ডিসকর্ডে আছে কিনা। ওকে। আর
এই ফিচারটা ডিসপ্লে আছে, তবে জুম ইজ মাচ ক্লিয়ারার এন্ড রেজলিউশনে ভালো আসে।
ওকে, গ্রেট, ইয়া। আই থিঙ্ক এই জুম ক্লিয়ার হওয়ার কারণ হচ্ছে বাংলাদেশেও কিছু জুমের সার্ভার আছে, লাইক ইটস নট লোকাল সার্ভার থেকেই করা হয় তো, এই কারণে আই থিঙ্ক জুমটা ক্লিয়ার হয়। ডিসকর্ডের সার্ভার বাংলাদেশে কয়টা আছে আই ডোন্ট নো।
না, আরেকটা খুব সম্ভবত আপনি যখন ইয়ে করেন, যখন নোটবুক অন করেন, যদি জুমে অন করেন তাহলে জুমেই নোট মানে জুমের সার্ভার নোটবুকটা অন হয় এবং আপনার পিসি থেকে হচ্ছে ইনপুট যায়, সেই আউটপুটটা আবার আমাদের পিসিতে দেখায়। কিন্তু
ওকে।
ডিসকর্ডে যেটা করে ওটা হচ্ছে আপনার স্ক্রিনটা ক্যাপচার করে, সেটা সার্ভারে যায়, সার্ভার থেকে আবার পুরো স্ক্রিন ক্যাপচারটা আরেকজনের পিসিতে আসে। সো আই থিঙ্ক দ্যাট টেক্স আ লট অফ ডাটা টু প্রসেস।
ইয়া, ইয়া, আন্ডারস্ট্যান্ডেবল। বাট আজকে আমি আসলে স্ক্রিন শেয়ারই করেছিলাম, মানে জুমের যে ফিচার আছে নোটবুক সেটা ইউজ করি নাই।
Oh, so in that case, it would be the same, but still, Zoom was much clearer.
Okay, okay. If it works for everyone, it's all no problem, I guess. Okay, so yeah. So thank you guys for joining and welcome to this program again. Hopefully, we'll get something done by the end of this program. Depending on, so এরকম হতে পারে যে ইন্ডিভিজুয়ালি হয়তো প্রজেক্ট অ্যাসাইন করতে পারি, অর গ্রুপ প্রজেক্ট, মিনিং দুজন দুজন করে আর কি, টু অফ ইউ উইল ওয়ার্ক অন দ্য সেম প্রজেক্ট, এরকমও হতে পারে। ইট উইল ডিপেন্ড, লাইক আমরা হয়তো কয়েক সপ্তাহ পরে ডিসাইড করবো যখন কোয়ান্টাম এক্সপ্রেস অ্যাকচুয়ালি শুরু করবো আর কি। ওকে, সো এই সফটওয়্যারগুলি ট্রাই করো, প্রবলেম হলে আমাকে নক দিবা, যে কোনো প্রবলেম। সি ইউ নিড টু লার্ন, রাইট? And I have also signed up, agreeing that yes, I'm willing to explain stuff. So hopefully we'll make progress. Let's see. Okay, take care. See you in next Saturday. Walaikum salam. If you don't have questions, you can leave, and I'm gonna close the meeting in a few seconds.